This is Trends in Binary Star Systems by Nicole Bartel, J.P. Caldwell, and Chris Folick.
When deciding on a topic, we were driven by the following question. Are there trends in the properties of stars that end up in binary systems? This topic piqued our interest since binary stars are very common in the galaxy, so by studying them, we would be learning about a large fraction of the stars in our galaxy. We plan on articulating our findings using HR diagrams with overlaid heat maps to reflect the temperature and luminosity trends we find and a histogram to display the distance between the stars in the systems. We expected to see two different sources of light with their own magnitudes, which will help us calculate their temperatures and luminosities, as we learned to do in our Stars and Galaxies course.
Here we have our selected binary systems and their accompanying useful data. As you can see, the stars are in the first column, chosen from a 1992 study by Bo Reiperth and Hans Zinnecker titled Visual Binaries Among Pre-Main Sequence Stars. The B magnitudes, V magnitudes, and parallax angles were found using the SIMBAD database, and the observation ID, exposure time, and filter data was found on the MAST database. From these numbers and observations, we were able to perform all the calculations needed to attempt to find any trends in the properties of binary star systems. Before doing these calculations, however, we need to talk about potential sources of error. While the data is all correct, there's a huge potential issue with the mass datasets that we overlooked and later realized in our results. This is the issue of CCDs and saturation. For example, here are our images for the Sirius system. As you can see, there are huge streaks in both of the images. In the left one especially, what this means is that the white pixels are all around the same count value, meaning that the CCD recorded too many photons at Sirius A's location and they bled into the surrounding pixels. Originally, we thought that we could just look at regions around these streaks and call it okay data, but as we found out later, we were orders of magnitude low on the counts that we should have been getting because many additional photons are lost and not counted. Therefore, as we will see in the next few slides, we only have lower limits on our binary systems, since we know that we should have more counts, but don't actually know how many more counts there should have been. So from all our hardships with this data, we would like to advise you to be very careful in the future with HST datasets of stars relatively close to Earth, as they can be very easily saturated.
The temperature for each star was one of the first calculations that we did. The B and V magnitudes were taken off SIMBAD, and using the equation shown here, the approximate temperature in degrees Kelvin was calculated and tabulated for each star. In order to calculate each star's luminosity, a series of measurements and data had to be collected. This data can be seen in the provided table. The first step was to go on to DS9 and record values such as counts and inverse sensitivity. The inverse sensitivity can be found in the header, while the counts were measured using DS9's analysis feature. The next step was to calculate the filter width in angstrom. Each filter that was used to observe the star systems was looked up, and the width was calculated by subtracting the max wavelength by the minimum wavelength. From there, we multiply the counts, inverse sensitivity, and filter width to calculate a flux with units of ergs per centimeter squared per second. This can easily be converted to watts per meter squared by multiplying by 100 squared to get the centimeter squared to meter squared, and dividing by 10 to the 7th, as that is how many ergs are in a joule. Now that we have flux for each source, we just need to convert our parallax angle from milliarc seconds to meters. This is done by first converting it to parsecs, and then multiplying by the amount of meters in a parsec, which happens to be 8.138 times 10 to the 16th. We now have all the needed numbers to be able to calculate luminosity in units of solar luminosities by using the above luminosity equation and dividing by the luminosity of the sun, which is 3.846 times 10 to the 26 watts. Due to previously talked about sources of error, all calculated luminosities fall well below the known values due to saturation in our images. The arrows are here to show that we have calculated the lower bound limit for luminosity, and that the actual location of each star on this graph falls above the plotted position. This plot may look familiar as it is a Hertzsprung-Russell or HR diagram with temperature in Kelvin on the x-axis and luminosity on the y-axis in solar luminosities. When plotted against each other, it can be seen that there's a positive trend. As temperature increases, so does luminosity. It is apparent that even with the sample size of only 10 stars, the same pattern that is observed on HR diagrams has began to appear here. We can see Sirius B is in the ranges where white dwarfs fall, and indeed, in fact, Sirius B is a white dwarf star. It can also be seen that the binary pairs LKH alpha and tau both have stars that resemble each other in temperature and luminosity. One trend that appears between every system, excluding VW Cha and SZ23, is the similarity in approximate temperature between stars in their respective system. Further research would be needed to see if this trend is common amongst binary star systems before anything can be said with certainty.
The calculations to find the orbital radii were pretty simple. Since we already had the parallax angles from Sinbad, we were able to convert them into a distance in parsecs using the distance equation shown here. Then, since we had two legs of the triangle, we headed to DS9 to find the angle between the two stars, or gamma in the equation and diagram. Finally, from the law of cosines, we were able to calculate the third and final leg of the triangle, the orbital radius. But what does this really mean for trends in binary systems? Well, in our small sample of 5 binary star systems, we found an interesting pattern. It seemed as though a lot of the orbital radii hovered in the 3,000 to 4,000 astronomical unit range. The other two systems were then polar opposites, with the Alpha Centauri system at 14 AU and DH and DI tau at around 50,000. We were definitely surprised to see these results, as we were expecting the orbital radii to be pretty well dispersed. Of course, with a sample size of 5, though, the dataset is way too small to find definitive proof of any trend here. But it is possible that we are onto something, and further research into this topic could answer this question.
When we started this project, we aimed to answer one question. Are there trends in the properties of stars that end up in binary systems? While binary systems are very common, it proved very difficult to collect accurate, relevant data, which made it difficult to find the number of sources we were hoping to analyze. Most objects that we found were not in the Sinbad database, which was our primary means of finding the B and V magnitudes and the parallax angles. We ended up finding 5 sources that were both in Sinbad and that we could analyze in DS9. These sources, unfortunately, provided saturated images, which gave us skewed results for values such as the luminosities. We know that these saturated images occur due to the limitations of CCDs and their sensitivity. Although we were not able to get the results that we wanted to provide us with the trends we were hoping to see, we were able to learn more about the imaging and data collection devices used to analyze objects in space and their limitations. If we were to do this project again, it would be helpful to have access to more databases so that we would not have to rely on one source for the magnitude and parallax values. It would also be helpful to have access to more research papers to help guide us to more binary systems we could use as viable sources to find trends.
Thanks for watching.